There's so much stuff in this bag. It's our magical mystery bag.
Ah. Thank you.
All right. Yes. You can play, but you can't win.
I'm on delivery.
Okay, sounds good. Yeah. Mm-hmm. Yes, of course. Oops. Yeah. Gotta get you a sharp pencil. So as a reminder, we live stream all of our events. And so if you are having trouble seeing the screen, you can tune into our YouTube live stream, and so you can look at the screen that way. Or if the screen turns off, you'll also have a better time seeing it on YouTube. $30. All right. Hello, everyone, and welcome to Astronomy on Tap number 105 on March 25th, 2026. This is 1 week later than our usual event date, but hopefully it looks like that did not cause many issues in turnouts. That's fantastic. Today, we will be hearing from first Peter Ferguson on the new cartographers, how the Rubin, Roman, and Euclid observatories are teaming up to map the dark universe. And after that, we'll be hearing from Chow on great balls of fire, meteors and meteorites in the past, present, and future. And also a reminder that our next Astronomy on Tap will be on April 22nd, right here at 7 p.m., as usual. All right. And as always, we'll get started with some astronomy trivia that is loosely themed based on the talks you'll be hearing from. So as you go through the talks, you may find some answers to the trivia. Our first question, and also I will read them out loud on the first run through, and then I'll go through them again for a shorter afterwards. You get 2 rounds of trivia just to really think about it. Question 1. In meteor physics, which parameter most strongly determines the altitude at which a meteoroid begins luminous ablation? Is it A, the entry velocity relative to the Earth's atmosphere? Is it B, orbital inclination relative to the ecliptic plane? Is it C, heliocentric semi-major axis of the object? Or D, longitude of the ascending node at entry? Now, these questions are also a wide range of difficulties, so if you don't get one of them, it means you may have a better shot at some other ones.
Strikes the atmosphere.
Question 2. In meteor trajectory reconstruction, what is the primary purpose of multi-station observations? This is observations from multiple different places. Is it A, measuring the chemical composition? Is it B, determining the pre-atmospheric orbit via triangulation? Is it C, estimating the meteor brightness? Or D, measuring the atmospheric density? Suspicious. Question 3. Which physical process dominates the light production of meteors in the atmosphere? Is it A, nuclear reactions, B, the reflection of sunlight, C, the ionization of atmospheric gases and ablated material, or D, gravitational heating? I'll give you a hint. It's A, B, C, or D. Yeah, happy to help. Question 4. Why are small impactors underrepresented in asteroid catalogs, but overrepresented in meteor observations? Is it A, because they are destroyed before detection? B, because they only orbit at night? C, because they move too slowly? Or D, because survey selection effects favor larger, brighter objects in space? Question 5. In entry modeling of meteoroids, what parameter most strongly controls whether an object produces a meteorite fall? Is this A, orbital inclination, B, the initial heliocentric distance, distance from the sun to the object? Is it C, the spin rate, or D, the strength and density of the object? We've now reached the end of our meteorite questions and are moving on to some lensing questions. In weak lensing analyses, what quantity is directly measured from galaxy images? Is it A, galaxy ellipticity, B, redshift from the spectra, C, luminosity distance, or D, velocity dispersion? And if you don't know what weak lensing is, you'll hear a lot about it in our first talk. Question 7. Why is the Roman telescope particularly important for complementing Rubin in dark energy studies? Some pre-talk spoilers here. Is it because A, it has a larger mirror than Rubin? B, because... Uh-oh. It just does this sometimes. It'll come back eventually. I did nothing. Thank you, though. Is it... Let me start over. Why is Roman particularly important for complementing Rubin in dark energy studies? Is it A, because it has a larger mirror than Rubin? B, because space-based imaging removes atmospheric systematics in weak lensing? C, it has a higher cadence than Rubin? Or D, it only observes nearby galaxies? Question 8. What is a key challenge in combining Rubin and Euclid datasets for cosmology? Is it A, different gravitational constants? B, different definitions of dark matter? C, a lack of overlapping sky? Or D, cross-survey calibration and systematic error control? Question 9. Which cosmological parameter is most directly constrained by combining weak lensing and galaxy clustering? Is it A, the Hubble constant alone, B, the stellar mass function, C, sigma 8, which is the matter clustering amplitude, this is how much stuff clumps together, or is it D, solar metallicity? And question 10. What is Rubin's primary advantage for time domain cosmology compared to Euclid? Is it A, higher spatial resolution, B, infrared coverage, C, spectroscopic precision, or D, high cadence, which enables transient and variability studies? All right, now I'm just gonna run through all of them again real fast to make sure you get a chance to look at them and think about them, and then we'll move on. Surprise, we're back at question 1. I already read them once. This time you have to use your imagination. All right, that has been the trivia segment of today's broadcast. Please, at some point, and by some point I mean now, please come up and give me your sheets and pencils. Please return the pencils. I need them back so I can keep doing this. They'll be graded, and then at halftime of our event, we will let you know the answers and let you know who the winner is. And then we'll switch over briefly to our first slideshow, and we'll get started right quick. Thank you. Now that our trivia segment is done, it is now my great pleasure to introduce our first talk, which is the new cartographers, how Rubin, Roman, and Euclid are teaming up to map the dark universe. This talk is by the wonderful Dr. Peter Ferguson, who got his PhD from Texas A&M and is currently a postdoc at the University of Washington. And also, his birthday was yesterday. So if you see him, make sure to tell him a happy birthday.
I was born.
Yeah. Have fun.
Cool. Okay. Let's see how this works. Okay. Well, thanks for being here and thanks for listening to me if you can hear me. And I'll try and speak up. Okay. So I want to give a brief introduction to myself because this is not what I'm talking about at all today. So I am a postdoc at the University of Washington, like Sam said. I study dark matter, but very nearby around our galaxy, the Milky Way. And I study these things called stellar streams that are objects falling into our galaxy. And I also do a lot of work building telescopes. So though I'm not going to talk about it, too close. Okay, thank you. Although I'm not going to talk about it, I got to spend a year in Chile, and that's a picture of me with Rubin Observatory, one of the ones I'll mention tonight. But when I wasn't up on the mountain at the telescope, I was spending time in La Serena, Chile. It was very beautiful, as well as up in the Elqui Valley. And so we do fun things as well as science. Okay, so what does mapping the dark universe mean? Behold our universe. Here's a distribution of where things are. You can see 5% is ordinary matter, 25% is dark matter, and 70% is dark energy. But we can see the 5%, but we can't see the other chunk of stuff. And so what we're trying to do is figure out ways that we can use that 5% we can see to learn about that big chunk of stuff that we can't see and isn't around us. Okay, so for this talk, we're going to define dark matter is things where we can see its effect. We can see the gravitational tug. but we've never detected it around us. And then dark energy is the universe is expanding. Things are moving apart, structure is growing over time, and it's accelerating. But again, that doesn't really mean anything to me or you conceptually. So how are we going to learn more? And the answer is going to be creating maps, which is why I called it the new cartographers. So what we would like is what I'm showing here from a simulation is a map of the dark matter in our universe. And you can see these areas that are glowing gold, and those are areas of really high density of dark matter. And you've got these dark filaments connecting everything, and then little voids that have nothing in them. And we'd love to see that, but we can't. So what can we see? So this is now showing from a different simulation, much smaller scale, sort of like our galaxy, the Milky Way size. And on the right-hand side is dark matter, and it's all over the place, and there's a ton of it. But on the left-hand side is what we can actually see. And so it's a really difficult question of how you go from what we think is there, this dark matter, even though we can only see what is going on here. And there's a lot of ways that people are doing that, and a lot of different tools people use. But today I'm going to talk about two different ones fairly quickly. One is called weak lensing, which is going to be talking about how much the dark stuff is there and how is it distributed around. And we can use it for that. And then also talk about a little bit about supernovae that we use to figure out how quickly are things moving apart from each other. I don't know how to fix anything. In doing nothing, I fixed it. Yeah, and so then we can also, I'm going to spend a little bit talking about supernovae. And then these two tools are the two things that these three observatories I'm going to mention are all kind of working on in complementary ways. Okay, so starting with weak lensing, which is like strong lensing, but weak. And so what I mean by that is, so the idea of strong lensing is you have a source here that's in the background. It's blue up there, so it's that blue arc. And then you have this lens, which is just like your glasses, and it focuses the light. And then the observer sort of sees multiple sources. And so even though there's one galaxy in the background, you see it as this blue arc that's smeared around. But you could imagine that if instead of getting smeared around a lot, it could get smeared a little bit. And that's what weak lensing is. And so, but you can't tell that by eye. So instead what we do is we have these catalogs of galaxies. And here's a bunch of galaxies. You can imagine them spread all over the sky. And we can measure the shape of each one of these galaxies. But we don't know how much mass is there. So we can't tell whether it's been bent or not at all. But what you can do is take the average of shapes. And on average, galaxies kind of look the same. Some of them might be squashed, but if you look at a bunch, you'll sort of average that out. And so then you can go from, where you have in different areas of the sky, these different galaxies, you can end up with something like this, where this is now showing the average shape of the galaxies in all these different areas of the sky. And this average shape is that lensing information, right? That if there's mass in between us, it's changed that average shape. And so this is a tool where we can take measurements of the shape of millions or billions of galaxies and sort of calculate their average shape as a position in the sky. And then that lets us get a handle on how much of that sort of lensing is going on there and how much their shapes are getting bent. And so you need to measure the shape of these galaxies, and then you also need to know some information about how far away they are, and we can use the color for that. So weak lensing, to sort of measure these mass maps. So what I'm showing here in purple is sort of looks like that simulation I was showing at the beginning. And the idea is that we were able to do this weak lensing measurement and sort of back out how much mass there is, bending the light of those galaxies, and then be able to create a map of that. And so we want to measure the shapes of the galaxies as well as their colors to get rough distances. And we want to do it for as many galaxies as possible. This is something where we really need the big data because this is a very small signal and it's very difficult to pull out that information. So that's what we're going to use to get a lot of our mass measurements and figure out the distribution of things. But that sort of is an angular scale. And the other thing that I want to mention that all of these observatories are looking at is supernovae. And so what supernovae are, they're these objects that a star, when it reaches the end of its life, it stops being able to push out or fusing elements, and it collapses and then explodes. And when it explodes, it gets very, very bright, and it can shine brighter than a galaxy. And when that happens, there's a very specific type of supernovae that is always the same brightness. And so we know exactly how bright it's going to be. And that means that if we see how bright we can observe it, we can figure out how far away from us it is. Too much? In the middle. Okay. Like this? That's too little, I feel like. There's like very little wiggle room. I'll try. Okay. So hopefully this works. So with supernova, we're looking at identifying these stars that explode and then being able to measure how bright they are. And then that'll give us a sense of how far away they actually are. And then we can see how much their light has been redshifted, which is how much the universe has expanded. And that tells us sort of how things are accelerating. And I know that's complicated. And it doesn't really matter for this talk, but basically you want to catch a supernova and identify that it's gone off. You see these bright points that the arrows are pointing to. Those are exploding stars that are brighter than the galaxy. And then you want to measure that brightness as a function of time. And you can see how they're all different down here. But then we can solve for how they truly are and sort of get this standard supernova. And so what we really want from these surveys is to be able to detect many, many supernovae and detect them at many, many different distances. So this is data that we've already had where I'm showing the amount the universe has expanded, or redshift, on the x-axis, and the distance inferred from the supernovae. And you can see that the yellow points, as we go farther away, the green line is going away from the blue line, which says the universe is expanding. And so we see hints of this, but we want to better understand it. So we need more supernova, and we need supernova that are further away from us. And so that is also something we are looking for. We want to detect all of the supernova at all of the distances. And so that, sort of brings things in, and we can so I briefly talked about tools we can use with this weak lensing to get sort of the mass measurements. And then the supernova give us a distance and how much things are expanding. And so if we put it all together, what we really want to make measurements of are galaxy shapes, galaxy colors, and detect as many supernova with as many different distances as possible. Great. So how do we do all that? And the answer, of course, is with telescopes. And so we've begun to enter sort of the golden age for this style of cosmology. And that comes with the Rubin Observatory, which this is a picture of Vera Rubin. She is one of the early astronomers who started discovering dark matter as a problem unknown, and she was looking at rotation curves around galaxies and found that this compelling need for this dark gravitational matter. And so we built a telescope and named it after her. And we finished construction of this telescope this last fall in 2025. And this has been a big part of my life for the last 5 years or so. And this telescope has the largest digital camera we've ever built on it, a 3.2 gigapixel camera. It's got a wide field of view, and it's got an 8-meter mirror, and that just means it can see very, very faint things over a large area of the sky. And it's going to observe the whole sky, well, 50% of the sky that you can see from the southern hemisphere, for 10 years. And what that's going to do is it's going to let us catalog 20 billion galaxies, which is 1% of the observable universe, And it'll also give us 20 billion stars. And so in the first year, we're going to catalog more objects than astronomers have cumulatively previously. So this is like the biggest catalog we've ever created. And we're going to, for all of these galaxies, get shapes of the galaxies as well as the optical colors of the galaxies. And so that really helps us with that weak lensing. We can start to get rough distances and also shapes. But Rubin, its real key is that because it can map the whole sky every 3 nights or so, we can find the things that change, that go boom in the night. And so Rubin is going to discover 10 million supernovae. Around 1 million of those are going to be good for this cosmology distance measuring I was telling you about. And each image that we take will have 150 active supernovae on it. And so we're going to be running for 10 years, and we're just going to get loads of these objects, and that's going to really help us get a better sense of the fine details of that acceleration that I was talking about earlier. And then there's also Euclid, which is a European Space Agency-led telescope that was launched in 2023. So it's about halfway through a 6-year mission. It's in space, which means that it can see things much sharper. The Earth's atmosphere sort of smears out light, which makes it very difficult to resolve little details or measure the shape of a galaxy. So it's really good at measuring shapes, and it's covering about 15,000 square degrees, which is about the same size as the Rubin footprint, but its mirror is not as big because it's expensive to put a big mirror in space, so it doesn't see quite as faint as Rubin does. But it will give us really good shapes for about 1.5 billion galaxies, and it also gives us near-infrared colors, which are really important for getting the distances to these, that you need both the optical colors as well as the near-infrared colors to be able to get these rough distances. And then that sort of tells you how far away this stuff that you're seeing lensed is from you, so you can figure out where that mass is in between you. And this is a picture of Euclid that was taken in a woodcut from 1530. This is what the satellite actually looks like, and it's in space. And then the last satellite that's coming online this fall is the Nancy Grace Roman Space Telescope, and it's named after Nancy Roman, who was an administrator at NASA, and she's really called like the mother of Hubble. She came up with this idea of the great observatories, where we would really push U.S. astronomy to put out these telescopes, and that instead of doing 1,000 different things, we were going to do one thing. And it's been these spectacular observatories like Hubble, Chandra, JWST. And so Roman Space Telescope is named after her. It's launching this fall, which is about 6 months ahead of schedule, and it's fully funded. It's going to be in space, although this is a picture I took from this summer. It's in a clean room in Goddard in Maryland right now. And you can see some people down here, and this bit is sort of all wrapped up and ready to go in space. And Roman is really good because it has a wide field of view, just like LSST, but not quite as big. And it has the best resolution out of all 3 of these telescopes. So it will be able to see the smallest little details. And sorry, I'm a little distracted. And so Roman will be really, really good at doing these weak lensing measurements where we're looking to measure the shapes of galaxies. That is where it's going to perform best. But it's not going to be as much of the sky as Rubin is doing. So Rubin's covering the whole sky over and over and over. Roman's just going to do 3,000 square degrees, which is, so Rubin is like 20,000 square degrees. So it's like 1/7 of the area, but much better resolution. And additionally, Roman was originally envisioned as a supernova telescope. Remember I said we wanted to measure all the supernova and at all the distances. And so it turns out that as you put supernova further and further away, the universe expands more and the light gets redshifted. And so at some point, you're no longer detecting the supernova in optical colors. And so you need the near-infrared colors to be able to detect these faint supernovae. And so Roman was really designed to basically look at a large area of the sky over and over and over and over and find all the things that go boom that are really far away. And so that's what it's really bringing to the table, in addition to having this really high resolution. And so with Roman, we're going to be able to probably detect around 27,000 type 1a supernova that we'll use for cosmology. And again, this is like 10 times the number we know right now. And these are all going to be way off of that plot that I was showing earlier. They're going to be further away. And then Rubin's going to add like another 1 million of those. And so we're really going to be in this era where we are able to combine all the data and learn a lot more about the universe because of that. And so here's just an example of what I was telling you about before, that this is a Rubin or an LSST image of an area of the sky on the right. These are both simulated. And you can see how everything's kind of blurry. And that's because the atmosphere will smudge that out. Whereas this is the exact same set of objects, but everything looks much sharper. So if we're worried about measuring the shapes of things and averaging that, you're going to be able to do a much better job with the Roman data than the Rubin data. But you need the colors from Rubin to be able to do all of these analyses with Roman. So it's really, everything's kind of working together. And I'm just going to restate that for galaxy shapes, Roman is the best, but it's covering the smallest area. For galaxy colors, you need both the optical and the near infrared. So Euclid helps with the near infrared, as does Roman, because Euclid covers a large area of the sky as well. We want to detect many supernovae at many different distances. And so Roman will help us get the most distant ones, but Rubin will really add on the most supernovae. But also science is really hard. And so we want a lot of independent measurements of these sort of things. We want to do these types of analyses with lots of different instruments so we can cross-check the results. And so that we don't have some error in one of them that makes us learn the wrong thing about the universe and make a mistake. And so by having sort of all three of these observatories together, we can really sort of tackle these hard problems and hopefully get sort of consistent answers from all of them. And it's really exciting because like we will be able to make this ultimate map of the dark universe. And we're like really in this era, like after these 3 experiments run, so the next 10 years, we're never going to do a galaxy shape measurement survey again. This is as good as it gets for that. After these experiments run, we're not going to do a distant supernova thing anymore. Roman is as good as we're going to get for that. And for optical supernovae, Rubin is as good as that's ever going to get. So like we're really in this era where this is like something, we've been pushing on these weak lensing experiments for the last like almost 25, 30 years now. And this is sort of the pinnacle of that. And so we're all just kind of waiting for the data to start flowing and start working on these analyses. So yeah, that's kind of what I wanted to talk to you guys about. Thanks for listening. Can we do questions? I've been advised that we can do questions if you guys have them. Yeah. The question is, how many supernova happen in the average galaxy per year? And I don't know in general, but I think the answer is 1 in the Milky Way every 100 years. But this is very far outside my actual field. Yeah. So the question was, why stop at infrared? And the answer is, as you go further, there aren't a lot of photons being emitted. And so the furthest we can see is something called the cosmic microwave background, which is in the radio. And you can get pretty far back. But like, so the ones I was talking about are what we call the near infrared. And like JWST does like the mid infrared or infrared and mid infrared. And that has more information too, but it's really hard to build. As you get redder and redder, you have to cool things better and better, and that becomes very difficult. So it's hard to do a big survey telescope that way. Yeah.
Rubin can't see the far away supernova from the direction. What's the distance limit?
Yeah. So the question was, if Rubin can't see those really far away supernova because their light has gotten redshifted and they're no longer in the optical bands, how far can Rubin see supernova? And I think the answer is out to a redshift of like 1.2. And I don't know what that is in useful human distance units because we always talk about it in redshift. But like Roman will go out to a redshift of 2. And I think like, oh, I'm a Milky Way astronomer, so I'm going to get this wrong. But I think like 2 is roughly half the lifetime of the universe. Or something like that. Yeah.
This will likely be interfered with by interstellar intergalactic. We really have an advantage since the infrared gets through all that stuff as far as
So you mean Roman. So the question was that dust can stop optical light, and it goes better, and light that is in the infrared is transmitted better through the dust. Does that give an advantage to telescopes like Euclid or Roman that use near-infrared observations? And the answer is yes, that there are a lot of things that they can see better, and that if you look equally faint, or if you find 2 faint things, you'll be able to see the fainter thing in the near-infrared because a lot of the light can get out, even if it's dusty. Yeah. The question was, do you know which spacecraft is taking the Roman telescope up? And the answer is, I don't know. But maybe someone else does? Yeah.
So what happens after 10 years with Rubin?
Right. So what happens after 10 years with Rubin? That's a great question. It's still going to be amazing at finding things that change at night. So some of us think we should just keep running it and keep seeing things that go boom, keep finding stuff in our solar system, keep looking for things that change, because then you can follow them up with other telescopes.
Is it a funding issue?
It's a funding issue. I mean, it's very expensive to run. Particularly the compute for Rubin is half of the cost of the experiment. And so we are spending a lot of money on processing all of the data. Yeah.
data is it generating in 10 years?
So the question was, how much data does Rubin or LSST generate in 10 years? And the answer is around, I think it's 50 or 60 petabytes of raw data. But then when you process it, it turns up into about a little more than half an exabyte of data that we will need to keep track of during the experiment. Cool. Thank you, guys.
Good job, Peter. Sorry. All right, now we are going to do the trivia answers, and then we'll take a quick break. But first, let's give Peter another round of applause. That's not what I wanted that to look like. All right, so some trivia answers. First of all, number 1, in meteor physics, what parameter most strongly determines the altitude at which a meteoroid begins luminous ablation? This is A, the entry velocity relative to Earth's atmosphere. Question 2, in meteor trajectory reconstruction, what is the primary purpose of multi-station observations? That is B, determine the pre-atmospheric orbit via triangulation. Question 3, which physical process dominates the light production of meteorites in the atmosphere? That is C, the ionization of atmospheric gases and ablative material. Question 4, why are small impactors underrepresented but overrepresented in meteor observations? This is because survey selection effects favor larger, brighter objects in space. Question 5, in entry modeling of meteoroids, what parameter most strongly controls whether an object produces a meteorite fall? This is D, strength and density of the object. In weak lensing analyses, what quantity is directly measured from galaxy images? This is the ellipticity of the galaxies. Question 7, why is Roman particularly important for complementing Rubin in dark energy studies? This is B, space-based imaging removes atmospheric systematics in weak lensing. This is very useful for cosmology purposes. What is a key challenge in combining Rubin and Euclid datasets for cosmology? This is also D, cross-survey calibration and systematic error control. Question 9, which cosmological parameter is most directly constrained by combining weak lensing and galaxy clustering? This was sigma 8, which is not something that we often think about in normal astronomy, but cosmologists love to talk about. And question 10, what is Rubin's primary advantage for time domain cosmology compared to Euclid? This is D, high cadence, which enables transient and variability studies. So those were the trivia answers. And there were a couple winners. And if you are one of the winning teams, please come up front during the break to collect your prize. Now, shockingly, there were 2 teams that got every question right, which is crazy. And those teams were Team Null and Void. Or is Team Null and Void? Nice. And the team, perhaps just a person, of Erica Chow. Good job. And we have one team get 9 points, which is Team Murphy. Good job, Team Murphy. So if you are one of those 3 teams, please come up during the break and you'll get a prize. And we'll reconvene in about 5 to 10 minutes with our next talk. Thank you all. Oh, that's basically it.
Because it's gravitational effect.
And you've plenty of time. If you go like 40 minutes, I'll probably cut you off.
It's like
All right. Welcome back from our little intermission. Our second talk of the night is going to be Great Balls of Fire, Meteors and Meteorites in the Past, Present, and Future. This talk will be by Ian Chow, who is a first-year grad student in the University of Washington's Astronomy Department. So one of my colleagues and perhaps even friends. Wow. All right, give him a round of applause. Enjoy.
All right, yeah. Hi, everyone. Thanks. As Sam said, I'm a student at UW. Thank you all for having me here. I'm very excited to be giving this talk today. So, as you might have guessed, my talk is going to be about meteors and meteorites. And specifically, I want to give this talk not just as talking about the science behind meteors and meteorites, although I will do plenty of that, but framed as framed around how people interact with meteors and meteorites and how they have done so throughout history. I think one of the really cool things about what I study, this is what I study, about meteors, is really that they're a part of astronomy that I think more so than almost anything else in astronomy is something that anybody, that the public, that you guys can all participate in, and that can all engage with. And I'll keep that in mind throughout, because I think there's a lot of opportunity for citizen science, for a lot of public outreach to be done, which I will talk about in the talk. So let's get on with things. All right, so before I get started, just a few terminology things about what meteors and fireballs and asteroids are, because I'll be talking about all these things throughout. So meteoroids are small rocks in space that are 1 meter in diameter or smaller. Anything larger than this is called an asteroid. This is the word of God. It was decreed by NASA in 2015 because the Planetary Defense Coordination Office, which handles asteroid impacts with Earth, and the Meteoroid Environment Office, which handles meteoroid impacts with Earth, could not agree on where their domains overlapped, and so they took it all the way to the very top of NASA, and they said 1 meter. And that's where the definition comes from. So a meteor, also known as a shooting star, is the event that's caused by the impact of a meteoroid or asteroid with the atmosphere, producing light, heat, sound, all these other phenomena as it passes through. And a meteorite is the object, the rock that you can recover on the ground sometimes, if part of a meteoroid survives its passage through Earth's atmosphere and reaches the ground. And a bolide or a fireball, which is, in the title of the talk, is just a name for a very bright meteor, anything brighter than about -3, which is about Venus's brightness. So, I think a lot of meteor showers, you can see these fireballs or bolides, although the ones I'll be talking about will be much, much brighter than this often. So let's start at the very beginning of meteors and meteorites in ancient times. So before, we did any science with meteors and meteorites, they were known to ancient peoples in a number of ways, often featuring in beliefs and in cultures. So I've given a few examples here. There's a passage from Virgil's Aeneid where Anchises, the titular hero Aeneas' father, talks about a shooting star that he saw over Mount Ida as an omen for the upcoming Battle of Troy. And then on the bottom, there's another astrological omen from the Babylonian Enuma Enlil, talking about what portends this meteor may bring. And on the right, that's the Willamette meteorite, which is a meteorite that was recovered in Oregon, that was first discovered by Europeans in Oregon about 100 years ago, and has since seen it is sacred to the indigenous peoples, of Oregon, and it was recently the subject of a long custody battle to get it back from a museum, where they recently agreed that I think about 10 years ago that the museum, it's in the American Museum of Natural History in New York, could hold on to the meteorite as long as it was open to the public. And also talk a little bit not just about the cultural impacts of meteors and meteorites in the ancient period, but also about physical and practical uses as well. So a big part of this in ancient times was the use of meteoritic iron, which is iron, which is, as the name suggests, iron from meteorites. And this is actually very unique because iron meteorites, which make up about 5% of all falls on Earth, are pure metal. They're made up of an alloy of mostly iron with some nickel. And unlike most iron found on Earth, which is in the form of iron ore, it is pure metal and so does not need smelting to be worked. And so that means that for a long time, a lot of metal objects, which were iron objects, which were very valuable, were made with meteoritic iron before people knew how to smelt iron. And so there's a few examples here. So on the left, this is a Tibetan dokcha, which literally translates to thunderbolt iron that falls from the sky. These are amulets that are traditionally made with meteoritic iron for protection, and to ward off evil. In the middle, this is an iron dagger owned by King Tut, the boy king, King Tutankhamun of Egypt, as some of you may know. And it was actually found to be made of meteoritic iron. They actually know this because they tested the content of the dagger, and they found that it was a lot of nickel in it, which would not be the case if it were made, which could only be the case if it were from a meteorite, which was relatively high nickel content. And on the right, this is a harpoon made from meteoritic iron. This is made with iron from the Cape York meteorite, which is a huge iron meteorite which fell in modern-day Greenland. And for centuries, Inuit people from around the region would travel and actually settle around this area where the meteorite fell. It's a huge meteorite, like 50 tons, and they would actually harvest it to create tools like this iron harpoon. So it's also moving on to the first ever meteorite fall recorded. This is the Enzisheim meteorite in 1492. It fell in the town of Enzisheim in what is now France, near the France-Germany border. And it's the first recorded meteorite fall, which is to say it is the first meteorite where we know where the meteor that produced it was actually seen and confirmed. So on the top, this is an illustration, a woodcut illustration of the fall of the meteorite by an engraver. On the right is the meteorite, which still exists today in the town's museum. And this is a description of the meteorite by Sigismundo Tizio, a priest at the time who saw it, and who described it as ein Zeichen seltsam Wunder, or a sign of a miracle. And what I think is really cool about this description is that it actually captures a lot of very interesting scientific aspects of meteorites that we still see today. So triangular. Sorry. Gotcha. So yes, triangular in shape, charred, the color of metallic ore. So the meteorites, as they fall, are indeed triangular. Many of them are. They have some of them is distinctive nose cone shape, as you see in the top left. That's created because as the meteorite passes through the atmosphere, and part of it ablates or melts away, it naturally creates the most aerodynamic shape for the meteoroid to pass through the atmosphere and ultimately to the ground, which is why it creates this aerodynamic nose cone. And charred, the color of a metallic ore, could refer to the fusion crust, which is basically a charred outer layer of the resulting meteorite that also results from this ablation as part of the meteorite melts and then again refreezes. Once it gets cool enough, it's slowed down enough that it's cool enough, and the part that is melted now refreezes, it often appears as this black glassy crust, which is amorphous rather than crystalline as the interior of the meteorite often is. accompanied by crashing thunder and lightning. So this is, this is likely referring to the sound of the meteor, which produces a sonic boom as the meteoroid passes through the atmosphere. These impact you very quickly and don't slow down enough if they're large to be below the speed of sound until they're very low in the atmosphere. So you can often hear the sonic boom from these. They're often recorded nowadays on infrasound or seismic stations as well, operated by by seismologists. They're often by military infrasound as well. So this is very low frequency sound where these sonic booms or even just the resulting air bursts as they fragment the atmosphere can be picked up. And of course, lightning, this is probably referring to the visible fireball as it passes through the sky, one example of which is in the right. And then it had split into several pieces where it had traveled at an oblique angle. So this is probably referring to the meteorite strewn field, which is essentially, as it says here, a field, typically ellipse-shaped, of where meteorites are likely to land for meteors. And it's oblique, and it's an ellipsoid because the entry angle is oblique. So here you can see an example. This picture on the bottom is for the 2022 meteor that fell over southern Ontario, and this one here is for Canyon Diablo, also known as Meteor Crater in Arizona. And finally, it flattened the Earth when it struck. So a lot of these meteors can do ground damage, as I will talk about later. It can flatten Earth. Some of these can create craters. Even relatively small asteroids impacting Earth can actually create craters, depending on their strength. All right, we'll skip ahead a couple more centuries now and go to Laglet in 1803. This is a meteorite that fell in France and is widely considered the birth of modern meteoritics. It's the first time that scientists had conclusively shown the link between meteors and meteorites. This was controversial in the scientific community at the time. A lot of people, you've heard stories, but a lot of people weren't sure whether these were real. And so there were lots of theories saying that meteorites were actually from volcanic eruptions, or they were from lightning fusing together dust in the atmosphere. People, weren't sure whether it was actually rocks falling from the sky. So this meteorite was investigated by Jean-Baptiste Biot, who was part of the French Academy of Sciences. For those of you who are familiar with physics, this is the same Biot as the Biot-Savart law is named after, that describes the change in current the change in magnetic field with an electric current, who made this link. And what I really love about this is that Biot's central argument as to why these rocks had to have definitively come from space is essentially the same argument that we make today, that modern meteor scientists make today. So his argument focused on preuves morales, or moral proofs, and on preuves physiques, or physical proofs. So his argument for moral proofs was that all these people who don't know each other at all, so it couldn't be hearsay spreading through a community, all roughly agreed on the events that happened of the meteorite fall, and physical proofs, looking at the actual meteorites themselves and comparing them to the surrounding rocks and the foundries and mines that he visited. So, jumping forward to the present day, when we look at moral proofs, we have we essentially still use the same methodology as Biot did, though maybe not the same tools. When we look at moral proofs or eyewitness accounts, this, for example, on the left is a list of eyewitness accounts from the Tagish Lake meteorite, which fell in northern British Columbia in Canada in 2000. And you can see that they took very, very detailed reports. This is actually from the scientific paper. And they took very detailed reports from eyewitnesses describing how describing the meteor and the meteorite fall. And on the right, you can see 4 frames of casual videos. Many of these meteors, even today, are recorded are recorded not by scientific instruments primarily, but by casual videos, often things like dash cams or security cameras. And you can actually do science with these. A lot of very important meteor science has been done from dash cam videos, from security footage, from Ring doorbells, right? This is this is how a lot of meteor science is still done today. So yeah, a lot of current meteor science still relies on contributions from the public, from people who saw a meteor fall, from someone who happened to have their Ring doorbell, on. And physical proofs. So the second part of Guillaume's argument. So while we don't, while the methods are still the same, obviously the tools are a little different. We don't go around looking at foundries and mines anymore, but we do still compare these rocks, meteorites, to other rocks both from Earth and other meteorites recovered from falls. So on the left, you can see this is a big indicator of whether a rock recovered is likely to be a meteorite. This shows the chemical composition. On the bottom is the oxygen, the abundance of oxygen 18, and on the top is the abundance of oxygen 17, which are two isotopes. And you can see that meteorites, which are on this the diagonal lines, CAIs and chondrites, have very different isotopic abundances than rocks recovered from the Earth and Moon. So that's one way we know how these rocks are in space. And on the right, we also look at the mineralogy. So on the top right, this is a slice of L'Aigle, the meteorite I was talking about earlier. And on the top left is another fall from Saint-Pierre-le-Vigier, which is another meteorite that fell a couple of years ago, coincidentally very close to L'Aigle, also in France. And you can see, for example, you can see the mosaic patterns. So these are basically the kind of jagged, broken fragments of different colors in both meteorites. And this mosaicism is characteristic of shock metamorphism typically caused by impacts. So you can actually see how much these meteorites have been affected by previous impacts by looking at these mosaic patterns and compare them to rocks in Earth. So all this is to say that the basic methods of Biot's time, though maybe not the tools, are essentially still those used today. Jumping ahead a little bit again, I'm talking a little bit about meteor showers. So this is maybe one of the most famous meteor showers in history, the 1833 Leonid storm. It's called that because it was an exceptionally active meteor shower. So this on the right is an illustration of what the meteor shower looked like. By some estimates, it was over 100,000 meteors per hour, which is on the order of 30 a second, to give you some scale. On the top, this is an entry from Joseph Smith's diary, the founder of the Church of Jesus Christ of Latter-day Saints, talking about his experience seeing the Leonid meteor storm. Right? It's a sign that the coming of Christ is close at hand. So most meteoroids are part of the sporadic background. The ones that I've talked about earlier have all been part of the sporadic background, which is essentially the baseline kind of background level of meteoroids that are just floating around the solar system. But often those that we are most aware of are from showers. So these are specific at specific times of year, where a lot of meteors will come from a certain place on the sky called a radiance. You can see that's the red circle. It's called a radiant because the meteors from Earth, the meteors appear to radiate from a point on the sky. And on the left, you can see this is a model of the sporadic background of the meteors. So most of them come from several sources: the helion, the anti-helion, and the apex, the directions of which are here. And the Leonids in particular are really interesting because they have spectacular storms every 33 to 34 years. Most of the time, they're not particularly notable, but every 33 to 34 years, because that's how long it takes the comet, which produces the dust that becomes the Leonids. That's how long the comet takes to orbit. So it crosses Earth's orbit and releases a fresh batch of dust every 33 to 34 years. creates these very, very spectacular storms, often, hundreds of thousands of meteors per hour. So the last one was in 2000, around 2000. The next one is in 2033. So hopefully in 7 years, there will be something spectacular to see from it. So this is often the part of the talk where I ask people to go see whatever meteor shower is closest, but unfortunately we're in a time of year that is not particularly close to one. We're right here, and these are the major meteor showers of the year. So the axis is the zenithal hourly rate, which is how many meteors you could expect to see from zenith. So basically with the radiant directly overhead from you on a clear moonless night. So the background is about 25. That's the black line that you can see throughout. And often, and the peaks are various meteor showers. So there are a few. Because there's no big one I can point you to, I'll just point you to, I think, some of the biggest ones throughout the year. The first one coming up is the Eta Aquarius, which is peaks around May 6th. There's Perseids on August 12th. This is probably the most famous, the most visible meteor shower every year. And it's definitely a great sight. I would highly recommend everybody see it at least once in their lifetime if you haven't already. There's the Orionids in October 21, centered around October 21, although the peak for that is quite wide, so there's actually quite a bit of time around the peak date when you can still see meteors. There are the Geminids on December 14th. That's a very sharp peak, but sorry about that. It's a very sharp peak, but the Geminids are a very fun meteor shower. It's, I think, one of the only major meteor showers that is not from a comet, but is rather from an asteroid. It's an active asteroid, 3200 Phaethon, that is that is releasing dust every time it passes close to the sun. And those are really fun. Some of them are green because the asteroid has different stuff in it than comets do. So I would also highly recommend seeing it. That's number 2 on the list behind the Perseids. And the last one are the Quadrantids, which are January 3rd. That's very sharply peaked, so you really have to go that night, or else you are probably not going to see it. But, yeah. And this is an animation showing, so Earth, you can see, is here going around this yellow loop. Every time it passes by a comet orbit that produces an active shower, you're going to see it light up, and on the bottom, it's going to show what showers are active. So most of these showers are active, but they're pretty hard to see. They can be pretty hard to distinguish from the sporadic background, especially if you're, especially if conditions are not great. If the zenith is not directly overhead, if the moon is bright, if there's light pollution, there's lots of different things. But you can see there are lots of meteor showers throughout the year as the Earth is going around the sun. I think we're coming up on one. We are. And the last kind of major meteor that I'm going to talk about, many of you may have heard of this, is the Chelyabinsk asteroid impact over Russia in 2013. This was notable because it was the largest asteroid to ever hit Earth the largest asteroid to hit Earth where we have observations of it. And it's actually the largest by quite a significant margin. So the impact energy is about 500 kilotons of TNT, which is about as much as a typical nuclear warhead. And at its peak, it was 30 times brighter than the sun from 100 kilometers away. There were people standing under this that got sunburns, that got eye damage, because just from looking at it, that's how bright it was. And yeah, on the right, you can see this is like another dashcam video showing the path of the meteor. And another reason why we have so much good data for this is because it happened over a very populated area. It happened over Chelyabinsk. It's a large city in Russia, so there's tons of like dashcam videos, like security videos, stuff like that. And it also caused quite a bit of damage. So as you can see, yeah, none of these people were killed. Nobody was killed, but there were about 1,600 injuries. So This caused quite a lot of damage. And this and other things kind of got governments interested in planetary defense or how to protect from an asteroid impact. So FEMA, the US Federal Emergency Management Agency, was involved in planetary defense starting in 2013. NASA established the Planetary Defense Coordination Office, PDCO, in 2016. Those are the guys that decided, the word of God, who decided that an asteroid was larger than 1 meter. And in 2022, NASA actually went and tested a kinetic deflection test, which is a fancy way of saying they smashed a spacecraft into an asteroid to change its orbit. It was called DART, the Double Asteroid Redirection Test. And on the bottom left here, you can see the last moments of DART as captured on camera before it smashed into the asteroid. It was a success. The mission went as planned, and they did successfully show that with enough advance warning, they could meaningfully alter the orbit of an asteroid, enough for it to miss the Earth with enough warning. There you go. And the other aspect of this is from meteoroids, so from much smaller objects, and the risk they pose to space infrastructure. There is a lot of stuff up there in space, not just science stuff, but also satellites, GPS satellites, telecom satellites, military satellites. There's lots of stuff up there, and at some point, NASA realized that meteoroids that hit Earth can also hit these things in space. So you can see up there, there's like a range, there's kind of the sweet spot of sizes of meteoroids that can cause damage to space infrastructure between about 10 to the minus 5 and 10 to the minus 1 grams that are both common enough and energetic enough that they can cause significant damage. You can see some examples of that here. So on the bottom left, this is a meteoroid impact on the James Webb Space Telescope mirror just after it was launched. Meteor scientists like to joke that everybody else is waiting for JWST observations to get them data. Our use is just looking at it as a collecting area for meteoroid impacts. That's the joke. But now, for all James Webb proposals as well, you have to justify if it is moving towards a dangerous area where a radiant of a meteor shower is coming from. You have to justify why you have to expose it to that level of risk. So it seems like they did pay attention to what we were telling them after all. And on the right, this is a Soyuz spacecraft leak on the ISS that was caused by a meteoroid impact a couple of years ago. It's leaking coolant, which is a big issue. And the Meteoroid Environment Office of NASA, the other side of the word of God definition of asteroids, was established in 2004 in response to the 1998 to 2002 Leonid showers. Those are the most recent storms that I was talking about earlier. At that point, NASA was very concerned that these storms would damage a lot of spacecraft, not just NASA, but the US Air Force as well, would damage their satellites. And so they established the Meteoroid Environment Office after that to properly quantify this risk and make sure that it wouldn't happen. So I'm going to talk a little bit now, finally, about kind of what's next, and especially what you can do. So one of the things that you as anybody can do is reporting fireballs. So this is as simple as what BO did 200 years ago, except instead of having to send a guy to go around with a pen and paper, interviewing residents of villages, we have the internet. So if you see a fireball, you can report it to the American Meteor Society or the International Meteor Organization. It's as simple as that. And these reports scientists do actually pay attention to these reports, and they are used to help determine meteorite trajectories, potential meteorite strewn fields. This is an example of this here is an example for the meteor over Ohio last week. This was a 2-meter diameter asteroid that hits Earth and broke up somewhere over Ohio. On the right, you can see these are all the reports of fireballs that the AMS, the American Meteor Society, got, and the blue arrow is where they eventually determined the trajectory was. And then this is the official map of the meteorite strewn field produced by NASA. The blue pixels are actually Doppler weather radar detecting meteorites falling from the sky because they can detect that. One of the other things that I think is really cool is the Global Meteor Network, which is a worldwide citizen science initiative, which many people at UW are involved in, to observe the entire sky for meteors. And essentially, it's a kind of distributed network of anybody who wants to put a camera on the roof of their house or anywhere else that is a using commercial off-the-shelf parts. And this, I think, is a really, really cool initiative and is probably one of the simplest and most effective ways to get involved in doing meteor science as anybody. On the top right, you can see the amount of coverage that the Global Meteor Network has. So a lot over, North America, over Europe. New Zealand is flooded with cameras. South Africa recently got its first batch of 4, which is awesome. They're expanding it all the time, and I think they might now be at almost a quarter of Earth's land area covered by these cameras. And a lot of science is being done with this. So this is a really cool plot that I have to show in the top left, showing all meteor radiance reported by the GMN, the Meteor Network, over the last month. You can see the circles are the radiance of known meteor showers. So right now there's not a huge overdensity for all of them, but when there's a big meteor shower and you look at this, you'll see there's there's a really big hotspot on all of those. And then on the right is the current meteor shower activity level from this morning, which is the baseline, as you might expect. And a lot of cool science, as I said, is being enabled by this. So just last year, we had the first GMN-enabled meteorites recovery from observations of a meteor. So this was a meteorite fall at Lake Tekapo in New Zealand that was tracked by GMN cameras and recovered by people on the ground right there. All right, and last but not least, I'm also going to talk a little bit briefly about what I do and how my research relates to this. So what I'm doing right now at UW as a PhD student is trying to predict these Earth impacts before they happen. So, seeing meteors and recovering meteorites is really cool, but wouldn't it be even cooler if we could see them in space before and then track where they're going to impact and then pick up those meteorites after? So that's my goal. That's what I want to do at UW. And to that end, there's a couple, I think, very effective instruments that are going to come online in the near future that I'm hoping to work with. One of these is the Rubin Observatory / Legacy Survey of Space and Time, LSST, which Peter has already told you about. For me, I'm mostly interested in using it to find Earth impactors, near-Earth objects, and potential Earth impactors. And the second is NEO Surveyor, which is a satellite that's going to be launched in late 2027 to survey survey near-Earth space for NEOs. These are primarily going to be larger than 140 meters. These are the really dangerous ones that NASA and the US government, as an act of Congress in 2005, directed NASA to find more than 90% of these large NEOs. But it's also going to find a lot of smaller ones that are going to produce meteors and meteorites as well, which I'm interested in too. And these are each going to discover hundreds of thousands of new NEOs, and many of these are going to impact the Earth. And one of the cool things that Rubin is going to do is, this is just recently from my work, Rubin should discover about 1 to 2 of these Earth-impacting asteroids per year. So on the top left, this is a set of large Earth impactors from 1994 to 2025 that have been reported impacting the Earth. What I did is I ran all of these impacts through a simulated observing cadence of the Rubin Observatory to see how many of these would Rubin have seen if it had been running at the time of impact. And the bottom right are the ones that it saw. And this is actually really cool because the previously predicted impactors, so there have been 11 impactors that have Earth impactors that have previously been observed in space and then impacted the Earth. Most of these are in the northern hemisphere, 10 out of 11, which is also where most of the observatories have observed them on in Arizona, in Hawaii, and Hungary. Those are where the observatories that have observed them are located. And on the right is the simulated observations from our Rubin simulations. And most of these are in the southern hemisphere because that's where Rubin is, in Chile. So Rubin is actually going to complement existing asteroid surveys in the northern hemisphere that look for these things very effectively and cover the southern half of the sky as well. And the other, I think, really cool thing is that because the time of discovery, because Rubin has a much deeper limiting magnitude than these other surveys, it's going to discover these objects earlier, about 1.5 days before impact on average, which doesn't sound like a lot, but is still much more than any previously predicted impact, all of which were less than a day. And with Rubin, we're going to expect to see, I expect to see about 2 to 4 of these objects per year observed in space before impacting the Earth. And my goal is sometime during my PhD to observe one of these objects with Rubin, do follow-up observations and track it, and then catch the meteor as it goes through the atmosphere and a meteorite on the ground. And that's what I hope to do. All right. Thank you all for coming and for listening to me. Yes.
What is the primary filter for why you can't see all of them?
The primary filter is Rubin. Sorry, so your question was, what is the primary filter for why Rubin can't see all of these objects? So there's a number of reasons for that. One is that it's not going to be detected before it impacts. Some of these impactors are pretty small and only become visible at Rubin's depth only a very short time before impact. So if it's not pointed exactly in that direction, it might not pick it up before it impacts the Earth. It's especially because Rubin requires 3 observations of the object on 3 different nights within a 15-day period. This is a pretty stringent requirement, and it's there to avoid false positives, which would otherwise completely overwhelm like detections of asteroids. Yes.
Do you think you detected something on aircraft potential impact?
Yeah, so the question was, are we coordinating with the FAA at all to let them know in case there's a potential impact? The answer is these are infrequent enough, these potential impactors, that are at least the ones that are observed in space before impacting the Earth. These are infrequent enough that they are kind of in a zone where we haven't really, this is not really something that we've explored yet, because it's something that happens pretty infrequently. The first one of these was only found in 2008, and it's really picked up since really only 2022, which is when the majority of these were found. But some of these have been at least observed from aircraft before. So the first one of these imminent impactors is what they're called in 2008 was actually observed. The meteor was actually observed by 2 pilots on a KLM flight over Sudan.
I have watched them go below the wing.
That's awesome. Yeah, that's awesome.
It's awesome to some people.
Yeah, I imagine it's a little scary to you. That's right. The sky's a big place. Yes. Where should we go to see meteor showers in Washington? Anywhere that's away from light pollution, really. Yeah, and clouds, that's right, yeah. So anywhere that's away from light pollution and from clouds. Some other things you can't really control, like the moon. If the moon is bright, you're just gonna see less because that's gonna wash out a lot of them. But yeah, anywhere without clouds and anywhere without light pollution. Yeah. Yes.
Like graph you showed with the different asteroids pulling outward. So Leo was like on average like really low. So you said so how come that Leo has like these like storms like every like 30 years, but like Perseids they stay like relatively high. Will they have is it like the sun, will it be like a Perseid or like other kind of stuff?
Yeah, that's a great question. So it was for the graph I showed earlier about the Leonids, why the Leonids are typically, on normal years, are comparatively much less active than the Perseids, even though there are these huge Leonid storms, and whether we expect to see something similar for the Perseids. So let me just pull it up here. Yeah, the answer to this is that it depends on the geometry of the orbits and how much dust that the comet actually produces every time it passes around. So the Leonids are typically quite low because the comet that produces them, Temple Tuttle, it passes very close to Earth's orbit, but doesn't release as much material as the Perseids. So that means that because it passes so close to Earth's orbit, just after it's released a batch of material, Earth is going to hit almost all of it. And so that's why you have these enormous storms. Whereas the comet that produces the Perseid, Swift-Tuttle, releases more material, but doesn't cross Earth's path directly and is more diffuse. So the material is more spread out. So it's more consistent year on year compared to the Leonids. Yeah. Awesome. Back to you, Sam. Yeah.
All right.
Yeah. Yeah, thank you. Yeah.
All right. Thank you all so much for coming to Astronomy on Tap number 105. And I'm pulling out my phone to check the date for the next one, so I can tell you right now. The next Astronomy on Tap will be on April 22nd, 2026, which is also coincidentally Earth Day, as my phone is telling me, which is fun. Also, as a note, if you're looking for places to stargaze or look for meteor storms, you can look up a light pollution map on the internet, and you can just look at a map online of the best places to find darker skies. Yeah. All right. Well, let's give our speakers another round of applause. Thanks, everyone, for coming. I will see you all next month. Please get home safely. Have a nice night.